In this age of VCRs, compact disc stereos, home computers, and yes, Star Wars, a lot of people might think of trucks as being pretty low-tech. Just good, solid machinery that can slug it out in the workaday world. Reliable, but decidedly low-tech. Well, that just isn't true. Beneath those rugged, functional hoods are sophisticated systems every bit as high-tech as anything you'll find under a passenger car hood. Don't forget, trucks and vans have to meet emission regulations, the same as cars. Their owners are just as interested in mileage and reliability as our passenger car customers, perhaps even more so, because of the strenuous life the average truck leads compared to an automobile. You are watching the first of a series of 4 Expertec videotapes that will describe the systems and systems operations of the engines that power these hard-working trucks and vans. We'll be covering 4 engines, the 4.3-liter V6 and the 5, 5.7, and 7.4-liter V8, all 90-degree Vs. Generally, the systems for these engines are identical, like peas in a pod. Where there are differences, I'll be sure to point them out to you as we go along. Okay, let's get started with the engine control systems. And remember, this is important. These discussions apply to all 4 engines, unless I tell you otherwise. The heart, perhaps I should say the brain of most of the systems on these 4 engines, is the ECM, short for Electronic Control Module. The ECM is a programmed microprocessor that constantly receives input signals from various engine sensors, in addition to certain reference signals. It uses the inputs to monitor engine requirements for optimum operating conditions. Then, with its programmed logic, the ECM generates output signals to the engine systems for peak performance. Specifically, the ECM's output signals control fuel delivery, ignition timing, air management, and exhaust gas recirculation, or EGR. It also controls the engagement of the transmission converter clutch and the manual transmission shift light. Now that, in somewhat simplified terms, is a brief overview of computer command control. Now, let's get more specific. Depth of knowledge of the various components is needed if you're to effectively troubleshoot and correct problems the first time around. And I'm sure you know how important that is to our customers. Let's begin with the various sensors that input data to the ECM. They include the coolant temperature sensor, or CTS, the manifold absolute pressure, or MAP sensor, the O2, or oxygen sensor, the throttle position sensor, or TPS, the vehicle speed sensor, or VSS, the electronic spark control, or NOx sensor. This is not used on the 7.4-liter engine. Additional input signals go to the ECM from the park neutral switch, the power steering pressure switch, the AC control signal, an on or off signal, EGR vacuum, a temperature control signal. 3 other signals round out the inputs to the ECM. They are the distributor reference that tells the ECM the crankshaft position and the engine RPM, the system voltage, and the fuel pump voltage. From the illustration, you can see that the ECM receives a tremendous amount of information about the state of the engine. After comparing and evaluating the information, the ECM then sends outputs to the various systems it controls by means of electrical signals. The receiving systems respond mechanically or electrically to operate the engine in a peak performance mode. One major objective of this mode is that the air-fuel ratio be maintained at 14.7 to 1, required for efficient catalytic converter operation. We'll talk about how this is done in a little more detail in tape 2 of this series. The output signals from the ECM we will be discussing are air management, exhaust gas recirculation, or EGR, electronic spark timing, fuel control, which includes the IAC, or idle air control, and the electric fuel pump, and the ESC, or electronic spark control. Other outputs from the ECM include transmission-related signals, such as to the transmission converter clutch, the TCC, the downshift control, or manual transmission shift light, air conditioning, and diagnostics, which we will hit heavy in the final tape of this series. As I mentioned before, depth of knowledge is extremely important in diagnostics. So now that you've had an overview of the ECM inputs, the ECM itself, and the ECM outputs, let's look in more detail at the input devices and how they work. To do this, let's begin with the throttle body injection unit, in this case, the TBI 220. It contains the throttle position sensor, or TPS. The TBI 220 is mounted on the intake manifold, where it provides the means for air and fuel delivery to the engine. The unit consists of three major casting subassemblies: the fuel meter cover casting with a pressure regulator, the fuel meter body casting with two fuel injectors, and a throttle body casting with two throttle valves, or TVs, an idle air control valve, or IACV, and a throttle position sensor, generally called the TPS. Let's begin our detailed look at sensor components with the TPS. The unit is mounted on the throttle body opposite the throttle lever. Its purpose is to sense the current throttle valve position and send this information to the ECM. In reality, the TPS is simply a variable resistor used to convert the degree of throttle opening into an electrical signal to the ECM. The ECM then reads the throttle position by comparing the signal to a 5-volt reference signal. It's pretty simple. The throttle position changes, the TPS resistance changes, and the ECM recognizes the new throttle position. I might add that with the throttle closed, the TPS resistance is high, so its output signal to the ECM is low, about a half volt. At wide open throttle, the opposite is true. Low resistance and a high output signal, around 4.5 volts. An end result is that the throttle angle, as positioned by the driver, signals the ECM what the driver wants to do: speed up, slow down, whatever. Another important sensor is the CTS, or coolant temperature sensor, located in a coolant passage in the intake manifold near the front of the engine. This is a temperature sensing device that, as the name implies, informs the ECM of the coolant temperature. As you probably know, that sounds like a job for a thermistor, a resistor that changes resistance with temperature changes. And that's exactly what the CTS is, a thermistor. The CTS receives a 5-volt reference signal from the ECM. The ECM then measures the voltage across the thermistor, or CTS, and of course recognizes from the CTS signal it receives what the coolant temperature is. The CTS resistance is high at low temperature, about 100,000 ohms at minus 40 degrees centigrade, and low at high temperatures, about 185 ohms at 100 degrees centigrade. By knowing the coolant temperature, the ECM is able to accurately control several engine functions: spark advance and cold start fuel delivery, for example. You will also see in tape 2, the fuel system, that the CTS plays a vital part in whether the engine runs closed or open loop. So much for the CTS, or coolant temperature sensor, for now. Next, let's talk about the MAP sensor. MAP. That means manifold absolute pressure. This sensor reads pressure changes in the intake manifold with reference to zero pressure. These changes result from engine load and speed changes. The pressure reading is accomplished by means of a pressure transducer within the map sensor. Here again, the ECM provides a 5-volt reference signal. Now, since the pressure transducer is a kind of variable resistor, the map sensor output back to the ECM varies with changes in manifold pressure. The sensor's output varies from about 1 to 1.5 volts when the pressure is low, up to 4 to 5 volts at wide open throttle, a high pressure condition. The ECM uses the map sensor signal to help it calculate the fuel requirements and spark timing to compensate for changes in engine load. Again, sensor output signals vary from about 1 to 1.5 volts at idle and 4 to 5 volts at wide open throttle. The map sensor has a second job to do for the ECM. It provides a barometric pressure reading with the key on and the engine off. The baro reading is used by the ECM to compensate for different altitudes. The voltage reading will be low at high elevations and up to about 4.5 volts at sea level. The map also takes baro readings for the ECM at certain calibrated throttle angles. The next sensor we will look at is the VSS, or Vehicle Speed Sensor. If it's electronic, it's in the transmission, and if it's mechanical, it's behind the speedometer. The VSS generates an AC voltage that has a frequency proportional to vehicle speed. As the vehicle's speed increases, so does the voltage frequency. The AC voltage signal is then routed to the VSS buffer. The buffer converts the AC signal to a series of on-off pulses, which the ECM uses to calculate vehicle speed. The pulses take place about 2,000 times per mile. Now, as the vehicle's speed increases, so do the number of pulses per second. The ECM outputs, based on the VSS inputs, are used primarily to control the idle speed, diesel fuel cutoff, torque converter clutch, and the manual transmission shift light. When we get into the fuel system in tape 2 of this series, you'll see more of how the VSS is put to work. The O2, or oxygen sensor, is the heavy hitter when it comes to controlling exhaust emissions. It's located in the exhaust manifold, where it can monitor the oxygen content of the exhaust gas stream. It does this by means of a chemical reaction with the oxygen that remains in the exhaust gas after it leaves the cylinders. The chemical reaction produces an electrical signal proportional to the oxygen concentration in the exhaust gas. It works sort of like a small battery. The signals range from 100 millivolts with a high O2 and a lean mixture to about 900 millivolts with low O2 and a rich mixture. Before any of this can take place, however, the O2 sensor has got to be hot, over 600 degrees Fahrenheit. The ECM knows when the sensor is ready by comparing its output voltage to a reference voltage window. When the sensor voltage either exceeds or is less than the voltage window, the ECM commands fuel delivery based on O2 sensor values. The signals from the O2 sensor are used by the ECM to establish what must be done to maintain the 14.7 to 1 air-fuel ratio, the optimum numbers for good catalytic converter operation. The ECM issues rich or lean commands to the TBI 220 injectors as they are required to make this happen. To finish up with the O2 sensor, I should add that in addition to the sensor having to reach 600 degrees, there is a short time delay after engine start before the ECM will recognize its signals. We'll talk more about this when we discuss open and closed loop engine operation in tape 2 of this series. The last sensor we will discuss is the electronic spark control, or ESC. The ESC system has two major components, the ESC module and the ESC knock sensor. The knock sensor is located in the engine block near the cylinders, where it can detect abnormal vibration or spark knocking in the engine. The ESC module receives the knock sensor information and sends a signal to the ECM. The ECM, reacting to this information, then adjusts the electronic spark timing, or EST, to prevent spark knocking. The ESC module sends a voltage signal, 8 to 10 volts, to the ECM when no spark knocking is being detected by the knock sensor. In this case, the ECM orders normal spark advance. When spark knock is detected by the knock sensor, the module turns off the circuit to the ECM. With the signal voltage at 0, the ECM retards the electronic spark timing to reduce the spark knock. Once again, the electronic spark control system is not used on the 7.4-liter engine. In addition to the sensors just reviewed, I mentioned earlier there were other inputs to the ECM, all critical to engine operation and performance. Sudden changes in engine loads require the ECM to make rapid changes in output signals. Simply turning on the air conditioner is a good example of a sudden load on the engine, a load that demands additional power at once. The air conditioner signal is also from an on-off switch, which is closed when the AC control is set at max, norm, bi-level, or defrost. The signal tells the ECM to adjust idle speed to meet the heavier engine load from the AC compressor before the compressor is engaged. The park neutral switch is another source of information the ECM can draw upon. It informs the ECM by closing to ground when the transmission is in neutral or park, a low engine load. When the transmission is shifted to a drive gear, the switch opens and the ECM uses this information to make a decision, in this case, to issue a command for idle airflow regulation. EGR vacuum is not directly sensed by the ECM. However, the ECM knows whether or not the EGR valve is operative because the ECM controls a normally closed solenoid in the EGR vacuum line. The ECM control of EGR is based on input signals from the coolant temperature sensor. Coolant must be about 25 degrees centigrade. Other inputs are the throttle position sensor in off-idle position and the map sensor. There is also an electronic vacuum regulator for EGR control in the circuit on both the 5.7 and 7.4-liter engines. Other inputs to the ECM come from the distributor, RPMs, and crankshaft positions. We'll deal with those in a lot more detail when we get into the ignition system. The last two ECM inputs are system voltage and fuel pump voltage. That covers all the input signals to the ECM in our group of 4 engines. Now, let's look at the ECM itself, the electronic control module. It's located in the passenger compartment. In the G van, it's under the driver's seat. In the M van, it's near the right kick pad, and in all others, it's in the glove box. Now, since we've discussed the various input sensors, we can now recognize that the ECM is constantly looking at the input data and, in turn, is constantly making decisions for output signals to control the systems that affect vehicle performance. In addition to controlling the fuel, spark, and emission control systems, the ECM also performs a diagnostic function for the system. It can spot operational problems and alert the driver with the service engine soon light, and in the process, store a diagnostic code or codes identifying problems to aid the service technician in making repairs. The ECM also has a learning ability that allows it to make corrections for minor variations in the fuel system to improve drivability. This is called block learn, and will be covered during the discussion of fuel systems in tape 2. All the vehicles with the V6 and V8 engines we are discussing here have ECMs with 3 parts for service. This type ECM is referred to as a GMCM. The 3 parts are the controller, or an ECM without a PROM. All calculations take place here. A PROM, or programmable read-only memory, is located under the access cover of the ECM. It's the engine for an engine and vehicle such as vehicle weight, engine, transmission, axle ratio, etc. Because the PROM contains specific data, it cannot be used in another type vehicle. The broadcast code on the PROM and the ECM should be the same on original equipment. The third item is a CalPack with specific calibration information. It's used to allow fuel delivery if other parts of the ECM are damaged. It, too, is located under the ECM's access cover. If the CalPack is removed, it will result in a no-start, no-run condition. One last item about the ECM. That's the ALDL connector. ALDL stands for Assembly Line Data Link. The connector is used for end-of-the-line checks at the car plant, but later remains in the vehicle as a powerful diagnostic aid to the service technician. It's wired directly to the ECM and is located under the instrument panel. The connector has terminals that are used to diagnose the system with jumper wires or a scan tool. When we get to tape 4, Diagnostics, we'll explore the ALDL in detail and the scan tool. So much for the ECM for now. Let's move on to electronic spark timing, EST. We all know the purpose of the ignition system of an internal combustion engine is to provide an electrical spark with enough intensity to ignite the air-fuel mixture in an engine cylinder. Doing this in an optimum manner is what the EST system is all about. Timing of the spark in relation to the piston's top dead center position is very critical. If the air-fuel mixture is ignited too soon before top dead center, the combustion pressure front will collide with the upward-moving piston and knock will occur. If the ignition spark comes too late, there is an appreciable loss of power and economy. In either case, excessive exhaust emissions will result. The ECM controls distributor spark advance, or spark timing, with the electronic spark timing system. To do the job of properly controlling ignition and combustion timing, the ECM needs to know the crankshaft position, the engine speed, or RPM, the engine load, determined by manifold pressure or vacuum, the atmospheric or barometric pressure, and the engine coolant temperature. The EST system consists of an HEI, High Energy Ignition Distributor Module, the ECM and wires to connect the two, and the module connectors. The distributor module connector has 4 terminals lettered A, B, C, and D, with each circuit leading to the ECM. We'll go over the 4 circuits by their function. Terminal A, called the reference ground low, is grounded in the distributor and is used to make sure the ground circuit has no voltage drop that could affect performance. Terminal B is a bypass terminal. At about 400 RPM, the ECM applies 5 volts to this circuit to switch spark timing control from the module to the ECM. Terminal C, or the distributor reference high, provides the ECM with RPM and crankshaft position information. And terminal D is the EST terminal. This circuit triggers the module. The ECM does not know what the actual timing is, but it does know when it gets the reference signal. It then advances or retards the spark from that point. From a diagnostic standpoint, it should be noted that if the base timing is set incorrectly, the engine spark curve will be incorrect. That concludes the explanation in general terms of the EST system. However, now that we've talked about the HEI system as a component of the electronic spark timing system, let's look at HEI in a little more detail. The HEI system uses several components to accomplish electronic spark timing: the distributor, the ignition coil, the ECM, the MAP sensor, and the CTS sensor. The distributor has no ignition coil as a part of the cap. The coil is mounted remotely. Also, there is no vacuum advance unit mounted on the distributor or centrifugal weights on the inside. It truly is an electronic ignition system. The components inside the distributor are electronic in nature, a pickup coil, and the HEI module. The pickup coil is a signal generator. As the distributor rotor element turns, the pickup coil creates a voltage signal that is sent to the HEI module. The pickup coil issues 3 reference pulses to the HEI module on the V6 and 4 on the V8 for each revolution of the crankshaft. The HEI module itself has 3 major functions to perform. We touched on them early in our discussion of the electronic spark timing system. Number 1, it converts the voltage signals from the pickup coil and conditions their waveform into a square form that the ECM can use. The ECM uses these signals to calculate engine RPM, determine crankshaft position, issue pulses to the TBI 220 fuel injectors, and generate the ignition coil spark signal. The second task of the HEI module is to act as a switch that activates above and below a certain RPM threshold. It's used to switch spark timing from programmed control to full ECM control. The third and last task for the HEI module is to fix spark timing to a predetermined advance curve. The module is programmed to do this. In tape 3 of this series, which deals exclusively with the ignition system, we'll review everything that has been discussed so far about EST, then continue for a more in-depth look at bypass mode operation, the EST mode, and spark advance lookup tables. Since this tape is intended to be an overall introduction to the GM 4.3, 5, 5.7, and 7.4 group of engines, we have 2 remaining systems to be discussed. They are the air management system and the automatic and manual transmission controls. We'll start with the air management system. I'm sure you are aware this system is used to reduce carbon monoxide and hydrocarbon emissions. It does this in 2 ways. By injecting air into the exhaust manifold, unburned hydrocarbons continue combustion, even after the exhaust gases leave the combustion chamber. The added air also brings the catalytic converter up to operating temperature more quickly when the engine is cold. The hardware for the system consists of a belt-driven air pump, an electric air control valve with relief tube, check valves, and the necessary plumbing to join the working components together. The pump, which has a centrifugal air filter on its inlet side, supplies air to the air control valve. This valve directs air to either the engine exhaust manifold or through its relief valve to the air cleaner. The air cleaner acts as a silencer. When the engine is cold or in a wide open throttle condition, the ECM energizes the solenoid on the valve and air is directed to the exhaust manifold ports. When the coolant temperature increases, the solenoid is de-energized and air is diverted to the air cleaner. At higher engine speeds, air is directed to the air cleaner through the pressure relief valve, even though the solenoid is energized. There should be no air going to the exhaust ports when operating in the closed-loop mode. During engine decel, when there is a rise in the manifold vacuum signal, air is also directed to the air cleaner. A check valve on the air injection pipe prevents backflow of exhaust into the air pump if there is a backfire or the pump drive belt fails. In the event the engine is operating under a rich condition or the service engine soon lamp lights, the solenoid is de-energized and the air goes to the air cleaner. The ECM switches the solenoid on by completing a ground circuit within the ECM. As the ECM sees the coolant temperature rise or the engine go to closed loop, it opens the ground circuit. With the ground circuit open, the solenoid is de-energized and the air goes to the air cleaner. Automatic and manual transmission controls. In the case of the automatics, we have the TCC system, or the transmission converter clutch, and the downshift control system. With manual transmissions, we have the shift light system. Let's look into what these are and how they work. The transmission converter clutch used on the 700R4 automatic transmission uses a solenoid-operated valve in the transmission. This couples the engine flywheel to the output shaft of the transmission through the torque converter. This reduces slippage losses in the converter, and that increases fuel economy. Control of the TCC apply solenoid valve is by means of a ground switch in the ECM. When the solenoid is energized, it moves a check ball in a fluid line and allows the converter clutch to apply if the transmission fluid pressure is correct, an item outside the scope of this tape. For more about the correct fluid pressure, see the information on internal transmission operation in your service manual. The ECM controls the TCC apply by looking at the outputs of several sensors. The coolant temperature sensor. The engine must be warmed up before the clutch can apply. The throttle position sensor. After the converter clutch applies, the ECM uses the input from the TPS to release the clutch when the vehicle is accelerating or decelerating at a certain rate. The vehicle speed sensor, or VSS. The brake switch, which opens when the brake pedal is depressed and de-energizes the TCC solenoid, and the pulse switch. This is a downshift fourth to third pulse switch, which opens the TCC solenoid circuit momentarily during a downshift. The other ECM-controlled system on automatic transmissions is the downshift control system. When operating a vehicle equipped with a THM 400 transmission at speeds below 70 miles per hour, a forced or detent downshift is possible by depressing the accelerator pedal fully. The ECM recognizes the rapid increase in map sensor voltage due to the drop in manifold vacuum, and it turns on the downshift control relay. The relay then sends battery voltage to the detent solenoid in the transmission, which opens an orifice and forces a transmission downshift. With the manual transmission, I mentioned the shift light system that was controlled by the ECM. This light on the instrument panel indicates the best shift points for fuel economy. The light is turned on by grounding a switch within the ECM. Well, there you have an overview of the 4.3 V6 and the 5, 5.7, and 7.4 V8. We've looked at the ECM and its input and output sensor network. We've covered the ignition system, once over lightly. And we've looked at the EGR, air management, and transmission control system. While quite a lot of material has been presented here, it's certainly within the grasp of the trained technician. Now, for anything you didn't clearly understand the first time through, well, that's the beauty of the Expertec tapes. Just rewind and run them again. The next tape, tape 2, will cover the TBI 220 fuel system, as used on the 4 engines we've been talking about. Hope to see you then. Fuel, the lifeblood of any engine. It has to be managed, And that's what this tape is all about. Fuel system operation. If you've seen tape 1 of this series, then you've already met up with the TBI 220. It's a major component of the fuel system used on the 4.3-liter V6 and the 5, 5.7, and 7.4-liter V8s. You'll also find you're already familiar with several other components of the fuel system. With this tape, we'll pull these pieces of information together, build on them, and by the end, you'll really know your way around the TBI 220 fuel system. Now, since we're covering 4 engines in this tape, I should tell you now, the fuel systems of all the engines are just about the same. Where there are differences, we'll be sure and point them out to you. Let's begin by getting our arms around what we mean when we say fuel system. Here's a diagram showing a complete fuel system. Let's walk through it together. You can see that it's made up of an electric fuel pump, or 2 pumps on dual-tank trucks. There is a 20-second pump run on all 7.4 and some 5.7-liter engines. On all others, it's only 2 seconds. Then there's the fuel pump relay, fuel lines, and an in-the-line fuel filter. When you turn the ignition switch to the on position, the fuel pump relay is energized, and that in turn closes a circuit, and voltage is applied to the fuel pump. If for some reason the relay fails, a backup circuit through the oil pressure switch can also energize the fuel pump. From the pump, the fuel travels through the fuel line and inline filter to the TBI, or throttle body injection unit. The fuel is under pressure from the pump, about 15 pounds per square inch. This means there is a more than adequate supply of 9 psi regulated fuel at all levels of engine demand. Now that we have the fuel at the TBI unit, let's take a moment and review the TBI 220. Its purpose is to provide a means of air and fuel delivery to the engine. The unit consists of 3 major casting subassemblies: the fuel meter cover casting with a pressure regulator, the fuel meter body casting with 2 fuel injectors, and a throttle body casting with 2 throttle valves, or TVs. The casting also has an idle air control valve and a throttle position sensor. By the way, you should never snap the throttle lever back against the stop like this. It bends the lever and can change the idle air up to 30%. Now let's get back to the fuel as it enters the TBI unit through a passage in the fuel meter casting. The fuel surrounds the inlet of the fuel injectors, which are solenoid-operated devices controlled by the ECM. The ECM energizes the solenoid and the magnetic circuit, then lifts a normally closed ball valve off its seat. The fuel, under pressure, is injected in a conical spray pattern at the walls of the throttle body bore above the throttle valve. The fuel, in excess of injector needs, passes through the pressure regulator before being returned to the fuel tank via the fuel return line. The purpose of the pressure regulator is to maintain a constant fuel pressure at the injectors at all times. It does so by controlling the flow in the return line. You might call it a calibrated bypass. If the regulator allows the pressure to get below 9 psi, poor engine performance can result. Too high a pressure can lead to some pretty unpleasant exhaust odors. The pressure regulator is serviced as part of the fuel meter cover on the TBI 220, so don't take it apart. You can't fix it. For service, replace the fuel meter cover assembly. We'll talk more about how the pressure regulator works a little later. That completes our walkthrough of the fuel flow path from tank to TBI with the excess fuel returned to the tank. But that's only a small part of the fuel system. Controlling the fuel flow is the more complex area of fuel system function. As with most everything else on today's engines, the fuel system is controlled by the ECM with its network of input and output sensors. Ideally, the ECM strives for one thing as it controls the fuel system. That is to keep the air-fuel mixture at 14.7 to 1 during normal closed-loop operation. Or, said another way, control the engine's combustion so that it uses 14.7 pounds of air to burn 1 pound of fuel. The 14.7 to 1 ratio is sometimes called a stoichiometric ratio. To do that, the ECM must rely on a variety of input signals from sensors and other sources to give it the information it needs to command the fuel system to perform at the 14.7 to 1 ratio. I'm going to assume that you've already watched and pretty much digested the information about sensors and the ECM in the first tape of this series. With that as a starting point, let's consider what the ECM has in the way of control of the engine. If you think about it, it only has three things it can actually do to command the engine's operation. One, it can vary the spark advance, as we talked about in tape 1. We'll talk a lot more about that in tape 3, ignition system operation. Two, it can change the amount of bypass air by cycling the idle air control valve, or IACV, a device on the TBI unit that allows more or less air into the mixture coming from the throttle body. I'll tell you about that one in just a few minutes. The third control the ECM uses to deal with the engine is the pulse width of the electrical signal it delivers to the TBI's fuel injectors. Let's talk about pulse width. What is it? Well, pulse width is the length of time an injector is energized. Lengthening the pulse width causes more fuel to pass through the injector because it's open for a longer time, and that enriches the fuel mixture. Shorter pulse widths make the mixture leaner. It's sort of like opening and closing a water faucet. If you open and close the faucet quickly, a short pulse width, you won't get much water. And if you leave the faucet on for a longer time, you'll get more water. Pretty simple, huh? That's about all pulse width means. I should mention here that air-fuel ratios greater than 14.7 to 1, which means shorter pulse widths, are called lean mixtures, and less than 14.7 to 1, meaning longer pulse widths, are rich mixtures. We'll see that at times the ECM may want to use these rich or lean signals for certain engine operating conditions. Now that we understand pulse width, the next logical question we might ask is, how does the ECM know what width to make the signal to the injectors? There is no one simple answer to that one. Many things enter into the ECM's decision on what width signal to send to the injectors. Factors as diverse as vehicle speed, altitude, extra engine load from the air conditioner, or transmission clutch engagement, and cargo weight all go to make up the equation the ECM must solve before it can send the correct pulse width to the injector. Now, to complicate matters, any or perhaps all of these factors will be constantly changing as the vehicle moves down the road and through traffic situations requiring constant accels and decels. The ECM, however, can keep track of what's going on through the networks of sensors constantly feeding it signals. Although we discussed the ECM's input sensor network in tape 1, let's just take a quick peek at it again to jog our memory. There was the coolant temperature sensor, the manifold absolute pressure sensor, the oxygen sensor, the throttle position sensor, the vehicle speed sensor, the knock sensor, and battery voltage. We also had the park neutral switch, the AC switch signal, and the distributor reference signal. You'll recall how all these input signals were used by the ECM to formulate output signals to the various devices controlled by it. We were talking about the IACV, or idle air control valve, a few moments ago. The IACV is located on the side of the TBI 220 throttle body and is one of the devices controlled by the ECM. Its purpose is to control engine idle speed while preventing stalls due to changes in engine load. It does this by controlling bypass air around the throttle valve. By moving a conical pintle valve in to decrease airflow or out to increase airflow, the IACV can control the amount of air moving around or bypassing the throttle valve. If engine RPM is too low, more air is bypassed around the throttle valve to increase the RPM. If the RPMs are too high, then less air is bypassed around the throttle valve, decreasing the RPM. The IAC valve moves in small steps or counts, 255 of them, for its travel from full in to full out position. Each step is commanded by a pulse from the ECM. During idle, the correct position of the IACV is calculated by the ECM based on battery voltage, coolant temperature, engine load, and engine RPM. If the engine drops below a specified RPM and the throttle valve is closed, the ECM senses a near stall condition. It then calculates a new IACV position to prevent the stall and sends pulses to the IACV for its new position. By the way, these changes in counts sent by the ECM to the IACV can be read with a scan tool plugged into the ALDL connector. Remember, the IACV affects only the idle characteristics of the engine. So much for IACV theory. We said earlier that when there was a difference between any of the four engines discussed in this series, we would mention it. The 7.4-liter engine uses a different TBI 220 than the 4.3, 5, and 5.7-liter engines. The TBI used on the 7.4 has a larger 51-millimeter bore throttle body. That allows for increased air capacity. The bore diameter on the other three is 43 millimeters. Along with this, the 7.4 unit has a new flange-mounted idle air control valve with an O-ring seal. The flange mounting offers better centering of the pintle, thus improved valve seating. Since there are some differences in pintle shapes, be sure you have the correct part number if you replace an IACV. You'll need it for proper pintle seating in the throttle body. The IACVs used with the 4.3, 5, and 5.7-liter engines are of the thread-mounted type. While we're dealing with the TBI 220 units, there are two other devices that are components on the TBIs that we should discuss. One is a sensor, the throttle position sensor, that makes a major input to the ECM. The other is the fuel pressure regulator. We touched on it briefly when we were discussing fuel flow through the fuel system earlier in this program. First, let's talk about the throttle position sensor, or TPS. We discussed it in tape 1. You'll remember that it was located on the throttle body opposite the throttle lever. Its purpose was to sense the current position of the throttle and send that information to the ECM. You'll recall it was simply a variable resistor used to convert the degree of throttle opening into an electrical signal to the ECM. The ECM then reads the throttle position by comparing the degree of throttle opening to a 5-volt reference signal. When the throttle is wide open, the TPS has a low resistance, and the voltage signal to the ECM is high, around 4.5 volts. Of course, the opposite is true with a closed throttle. The TPS resistance is high, and the output voltage to the ECM is low, about 0.5 volt. It's pretty simple. The throttle position changes, the TPS resistance changes, and the ECM then knows the new throttle position. Now, let's talk about the pressure regulator. We said earlier in this program that the fuel pressure regulator is used to maintain a constant pressure at the fuel injectors at all times. We said it does this by controlling the flow in the fuel return line. We also said if the pressure gets below 9 psi, we get poor engine performance. And if it's too high, we get bad exhaust odors. If it does all that, we really ought to know about how it works. The pressure regulator is a diaphragm-operated relief valve with injector pressure on one side and air cleaner pressure on the other. It maintains a constant fuel pressure at the injectors by controlling the flow to the return line with the compression spring back diaphragm. If the fuel pressure gets too high at the injector inlet, the pressure against the diaphragm compresses the spring and fuel is allowed into the return line to the tank. When the pressure drops sufficiently, the spring pushes the diaphragm closed against the return line orifice, shutting off the flow of fuel to the tank. That covers the hardware of the TBI 220, except for the fuel injectors. They are the heart of throttle body injection of fuel into the engine. Incidentally, the 4.3-liter TBI uses a different injector with a different flow rate in each throttle bore to improve emissions. Be sure to use the same part number for repairs. Though there are 2 injectors on a TBI 220, let's look at a cross-section of only one and see how it works. We've already seen how the injector is a solenoid-operated ECM-controlled device. When the coil is energized, the ball valve is lifted from the valve seat. Fuel enters through the filter, passes through the injector spray tip, and onto the walls of the throttle body. Frequency and width of pulses to the injector coil control the fuel flow. The frequency, or number of pulses sent to open the injector, is tied to the number of pulses sent to the ECM by the distributor HEI module, along with other input signals. The width of the pulse is also controlled by the ECM. What we need to discuss now is how the ECM gives the proper pulse width command under all engine operating conditions. These conditions are called modes, and there are several of them. The various modes are the starting mode, the clear flood mode, the run mode made up of the open loop and closed loop modes, the acceleration mode, the deceleration mode, the battery voltage correction mode, and the fuel cutoff mode. 7 of them in all. Let's go through them one at a time. The starting mode commences with the ignition key being turned on. The ECM then turns on the pump relay for 2 seconds, and the turbine-type pump builds fuel pressure to the TBI unit. If there are no distributor reference pulses after 2 seconds, the pump is shut off. That number is 20 seconds on the 5.7 and 7.4-liter engines. Based on information from the coolant temperature sensor, the throttle position sensor, the manifold absolute pressure sensor, and the distributor crank signal, the ECM then calculates the proper air-fuel ratio for starting. That sounds like a lot of things have to happen just to start the engine, but they do happen, and almost instantly. Typical air-fuel ratios for starting run from 1.5 to 1 at minus 33 degrees Fahrenheit to 14.7 to 1 at 201 degrees Fahrenheit. Of course, the width of the pulse from the ECM controls these ratios. The clear flood mode is used when the engine is flooded. First, the accelerator pedal is fully depressed. That's indicated to the ECM with the throttle position sensor. The ECM then pulses the injectors at a 20 to 1 air-fuel ratio. It holds this lean rate as long as the throttle remains wide open and the engine RPM is less than 600. When the throttle position becomes 80% or less of wide open position, the ECM returns to the starting mode. Once the engine is started, the ECM goes into the run mode. This mode has two conditions, open loop and closed loop. We'll discuss what each of those terms means. The open loop condition occurs when the engine is first started and after it's running at over 400 RPM. In open loop, the ECM ignores the input from the O2 sensor and calculates the air-fuel ratio based on the coolant and MAP sensor inputs. After starting, the system stays in open loop until three conditions are met. First, the O2 sensor must show a varying voltage output. That indicates it is hot enough to operate properly. Second, the coolant temperature must be above a specified level as indicated by the coolant temperature sensor, or CTS. Third, a specific amount of time must elapse after starting the engine. The specific values for the three conditions vary with different engines and are stored in the PROM, located in the ECM. Once these three conditions have been met, the ECM is ready to run the engine in closed loop. In closed loop, the ECM calculates the air-fuel ratio based on the signal from the O2 sensor. This results in the air-fuel ratio staying very close to the desired 14.7 to 1. Now, keep in mind, the ECM does this by varying the length of electrical pulses it sends to the fuel injectors in the TBI 220 unit. By the way, during idle, the 7.4-liter engine runs in an open-loop condition. The 4.3, 5, and 5.7-liter engines idle in closed loop. The next modes we'll discuss are the acceleration and deceleration modes. I've grouped them together because the ECM does some special things with its output signals to the injectors in these modes. Remember when we talked about pulse width earlier in this session? We said the pulse width was the length of time an injector is energized. And the wider the pulse width, the more fuel that will pass through the injector. Now, I'll tell you the rest of the story about pulse width. It goes back to how the ECM knows how rapidly to issue the pulses. The ECM receives what we call reference pulses from the distributor and uses these pulses to initiate command pulses to the injectors. Since the command pulses are based on the distributor signals, they are uniform in timing and change timing only when the engine RPM changes. These are called synchronous pulses. During acceleration, the ECM sees a rapid change in throttle position and manifold pressure. The engine needs more fuel than the synchronous pulses can provide. The ECM commands extra pulses, totally independent of the distributor reference pulses, and the engine has the extra fuel it needs to continue the acceleration. These are called asynchronous pulses. During a decel, the fuel remaining in the intake manifold can cause excessive emissions and backfiring. Here again, the ECM sees a rapid change in throttle position and manifold pressure. This time, the problem is too much fuel. To obtain the required lean air-fuel ratio, the pulse width becomes very short, often less than 1 millisecond. With the pulse width that short, the injectors can no longer open and close fast enough to maintain accurate fuel delivery to the engine. The ECM handles this by adding up all the extremely short pulse widths until the total width exceeds 1 millisecond. It then issues an asynchronous pulse command to the injector. In the case of fast decels, the ECM can shut off the fuel completely for short periods. Fuel flow returns as the vehicle's speed drops below a preset limit so as not to stall the engine. Another mode that we listed before is the battery voltage correction mode. As the name implies, the ECM can compensate for a weak battery, which results in a weak spark from the distributor. It does this in two ways. It increases the injector on time, and it increases the idle RPM. There are times when it is desirable to cut off fuel to the engine, and the ECM is programmed to do just that. It's called the fuel cutoff mode. For instance, no fuel is delivered by the injectors when the ignition is off. This prevents dieseling. Fuel is not delivered when there are no reference pulses from the distributor. There is no need for it because the engine isn't running. Fuel cutoff can also be commanded by the ECM because of high engine RPM. It does this to protect internal engine components from damage. That concludes our discussion of the 7 modes of ECM engine operation. It would also conclude this tape on TBI 220 fuel system operation, except for one thing. As with any other complex device, everything isn't perfect all the time, and so it is with the fuel system. Parts wear a little. Orifices get a little dirty. You know what I mean. You see this stuff every day. While not brand new, the system is more than useful and perfectly capable of many more miles of trouble-free life. The only thing is, the ECM still wants to always maintain that perfect 14.7 to 1 air-fuel ratio. Well, that brings us to the ECM solution to the problem and our next subject, the integrator and block learn memory. Think of the integrator as being a means of providing short-term pulse width corrections for the injector signals. That's all. Under certain conditions, the block learn memory may then take the integrator's short-term corrections and permanently retain them as long-term corrections. These 2 items are parts of the ECM circuitry. Let's take them one at a time. The integrator responds to short-term changes in the air-fuel ratio by issuing rich or lean commands, making the injector pulses longer for richer and shorter for leaner. The O2 sensor tells it which way to go. The integrator is set up with a value or count of 128. This is a no correction value and equates to a 14.7 to 1 air-fuel ratio. Integrator values of less than 128, as provided by the O2 sensor, result from a rich condition, and the pulse width has to be shortened. Values over 128 mean a lean condition exists, and the pulse widths have to be lengthened. You can see how the integrator can be quite busy making small corrections, so the air-fuel ratio always averages 14.7 to 1. I should add, the integrator is only active during closed-loop operations. If the integrator has to consistently make a change of significance in one direction, block learn memory comes into play. To understand how this is done, we have to look at how block learn memory is set up within the ECM. The term block learn refers in part to the way it's divided into individual memory blocks within grids. The block learn structure for the 4 truck engines we're looking at provides 16 variables that will be referred to as block learn memory cells. The 16 cells are located in a 4x4 grid with map, or let's just call it load, on the vertical axis. The horizontal axis shows engine RPM. You can see that any combination of engine RPM and load falls within one of these cells. For example, an idle speed of 1,000 RPM and no load is represented by block 1. The blocks cover every engine condition, from low engine speed with no load in the lower left-hand corner to high engine speed and maximum load in the upper right-hand corner. Each of these blocks has an assigned pulse width correction for the amount of fuel required to be delivered for that particular engine condition. Like the integrator we just discussed, each block is assigned a value or count of 128, which represents an ideal 14.7 to 1 air-fuel ratio. Now, let's suppose the integrator, under some engine condition of RPM and load, is always making a correction, say from 128 count to 135. After a given number of excursions to 135 over a given time, the memory cell in block learn for that set of conditions changes its own memory on a long-term basis from 128 to 135. From then on, the ECM command for that engine condition is always taken care of with a 135 command. Once the permanent change is learned by block learn memory, the integrator will return to 128 count. It will not have to change again under the engine conditions that previously had been making it go to 135. You can see that changes in block learn memory cells from 128 to a higher or lower value signify that a long-term shift has occurred in the system. Changes in block learn of even 20 or 30 counts don't necessarily mean there's a problem. Expected normal engine wear could be the reason. However, when we get to tape 4, Diagnostics, you'll see that looking at block learn memory with a scan tool can be a very valuable problem solver. Just to recap the integrator and block learn memory, remember, these two items are part of the electronic circuits within the ECM, not a chunk of hardware somewhere under the hood. The integrator provides short-term pulse width corrections, while block learn memory, in some cases, takes the integrator's corrections and makes them a long-term part of the ECM's output to the injectors. One last item on the subject. If you disconnect the battery, the learned outputs disappear. However, that's not all bad. The ECM will relearn the outputs with a little driving after the engine has warmed up to temperature. Okay, that wraps up the fuel system and its operation. Assuming you have watched tape 1, had an overview of the 4.3, 5, 5.7, and 7.4 liter engines. You know how much they are the same. You also know of a few differences between their systems, differences generally found with the 7.4. You've been through the fuel system in a fair amount of depth with this tape. The next tape in the series, tape 3, is called Ignition System Operation, and it will cover the same 4 engines. It'll describe such things as electronic spark timing, the HEI distributor, HEI system operation, spark advance lookup table, well, the whole system. We'll save the talk on that until tape 3. Now, tape 3, the ignition system operation, will give you even greater knowledge of the 4.3 liter V6 and the 5, 5.7, and 7.4 liter V8 truck engines. Hope to see you then. Plug. That's what it's all about. The whole ignition system is built around it, making it fire at the right time for maximum power and minimum emissions. And that's what this program is all about. Any ignition system for an internal combustion engine has but one purpose. That is to provide an electrical spark intense enough to ignite an air-fuel mixture inside an engine cylinder. And that spark has to be timed just right. The best possible engine performance, drivability, fuel economy, and emission control depend on precise spark timing. With today's ECM running things, engine-wise, it's no surprise to learn it controls the ignition system along with just about everything else under the hood. It does this with electronic spark timing, or EST for short. In this program, tape 3 of our Expertec series, we'll cover the components of the ignition system and how they work, the system itself and how it works. We are dealing with 4 truck engines, the 4.3, 5, 5.7, and 7.4-liter group, all equipped with the TBI 220. In most cases, the ignition systems for these engines are the same. Where there are differences, I'll be sure and point them out to you. Let's start with a broad overview of the ignition system, just to get a feel for what we're dealing with. We've said that precise spark timing is very important. Let's look at why this is so. Spark timing refers to the point in the compression cycle at which the spark plug is actually fired. It is measured in degrees of crankshaft rotation relative to top dead center. That's the point where the piston reaches its full upward position within the cylinder. When the spark plug fires, rapidly expanding combustion gases fill the cylinder and create extremely high pressures. Should the spark begin the combustion process too soon, the combustion pressure front collides with the upward moving piston and knock or detonation occurs. If the spark comes too late, well, the piston is on its way down, the high compression of the air-fuel mixture is lost, and worst of all, power is lost. Not only that, exhaust emissions will probably go to pot too, either with the knock or the late firing. Other things can affect spark timing in addition to piston position. Examples are air-fuel mixtures that are either rich or lean. They affect burn rate. Engine temperature also affects timing. The EST is responsible for keeping track of these variables and for combining sensor inputs with stored data. It then is able to trigger accurate spark plug firing for all engine operating conditions. There are two ways or modes in which the ignition system works. Let me just cover them quickly for now. The first is the bypass mode, in which the ignition timing or spark advance and dwell are controlled by the distributor. This mode occurs during starting or cranking of the engine. It's also used in the event the second mode, the EST mode, fails. We'll talk in more detail about the bypass mode later. The second mode, and the one used by the engine most of the time, is the EST mode. EST means electronic spark timing. It's the engine running mode, and it's controlled by the ECM. As you know from the previous tapes in this series, the ECM can only function when it's supported by a network of sensors. It needs their input on the state of the engine before it can decide on and issue commands to whatever system it is controlling. In this case, it's the EST mode of the ignition system. Let's see what components go to make up the EST system. They are the ECM itself, the distributor, the coolant temperature sensor, the MAP sensor, the battery, the ignition switch, and the electronic spark control module, or knock sensor, except on the 7.4. Okay, we said we would come back to the bypass mode of operation. That's a good place to begin because that's when the engine starts. When the ignition key is turned to the start position, the starting motor relay is closed and the engine is cranked. With the engine being turned over, the pickup coil in the distributor starts sending reference pulses to the HEI module, also in the distributor. It sends 3 pulses for each revolution of the crankshaft on the V6 and 4 pulses on the V8. The module then converts these signals to a square waveform the ECM can use. Upon receiving these signals, the ECM is aware of the engine's RPM and crankshaft position. As long as the engine is cranking at 475 RPM or less, a below-run condition is sensed. We are now in what is called the bypass mode. The ECM sends a pulse to the injectors for each reference pulse it receives from the HEI module so that there is an air-fuel mixture in the cylinders. At the same time, it also holds the bypass line voltage at about 0.2 of a volt, too low to energize the solid-state switch that allows ignition operation in the EST mode. That puts the HEI module in control of spark timing, which provides a ground path directly to the primary side of the ignition coil at the base timing setting of the distributor. Once the engine starts, the RPMs climb immediately. The ECM, sensing the run condition from the pickup coil signals, increases the bypass line voltage to 4 or 5 volts. When the HEI module sees this increased voltage, its solid-state switch responds like a relay. It switches the spark timing function from the pre-programmed bypass control to full ECM control. Full ECM control means the ignition system is in the EST mode of operation. In that mode, timing changes are issued in response to changes in input signals to the ECM. Let's check out some of these inputs. On our list of EST components we showed a while back, we have the manifold absolute pressure sensor, or MAP sensor. You'll recall that device converts manifold pressure to a voltage, defining engine loads that the ECM can recognize. Then there is the CTS, or coolant temperature sensor. As the temperature of the sensor changes, its resistance changes. Remember how it works? The ECM supplies a 5-volt reference signal to the sensor and measures the voltage drop across the sensor. Another constant input to the ECM is the reference signals generated by the pickup coil in the distributor. Those signals give the ECM a continuous monitoring of engine RPMs. The flow of signals from these 3 sources is used to look up information stored in the ECM in a programmed memory. We've talked about that stored memory in earlier tapes. Remember the PROM? The PROM, which stands for Programmable Read-Only Memory, was located under the access cover of the ECM. We said it was the engine calibrator and had specific program information for an engine and vehicle, and it applied only to that vehicle. Some of that stored info is for spark timing. The information is stored in what we call lookup tables. On the truck engines we're talking about, there are 4 lookup tables, each one with a spark advance value based on 2 variable inputs. Let me show you how that works. It's not hard. In fact, it's kind of interesting. We'll do it with this diagram. The first table provides a spark advance value based on load and RPM, or if we want to get technical, MAP sensor signals and distributor reference pulses, okay? This value modifies spark according to load. The second table is for coolant temperature and manifold pressure. It issues a second spark value, retard for hot, advance for cold. This time, the sensors involved are the MAP sensor and the CTS, or coolant temperature sensor. Table 3. This one looks at engine vacuum and RPM and issues a third spark value. The MAP sensor takes care of the engine vacuum signal. That's done by finding the difference between manifold absolute pressure and barometric pressure, the baro being taken by the MAP sensor with the key on and the engine off. The engine RPM, like in Table 2, is given by the distributor reference pulse. This table value compensates for any EGR that may be present in the air-fuel mixture. Finally, there is Table 4. It looks at barometric pressure and engine vacuum, then issues a fourth and final spark advance value. This one is to compensate for altitude variations. This work is all done by the MAP sensor. Okay, we've got 4 signals for spark advance based on 4 lookup tables. What happens now? Well, they are electronically added together, and the total provides the correct spark advance for all engine operating conditions. The ECM issues commands for that amount of spark advance. That's what EST is all about. Electronically controlled spark timing. It keeps drivability up to performance standards, and it keeps the emissions low. Even the best designed and built devices sometimes go sour, including the EST ignition system. Now what happens? Remember the bypass mode used when the engine was being started? Well, if something goes wrong with the EST system, the ECM will direct the bypass voltage to drop. That, in turn, will make the switching circuit in the HEI module switch to the bypass mode, the same circuit we started the engine with. The engine will run that way, and you can drive the truck, but you probably won't like it much. However, it will get you home. I'm sure you've all had trucks brought to you in that condition. Now, one other thing, while we're on the subject of ignition system repairs, just a quick tip. If the engine won't start or just quits running, be sure and check if the distributor pickup coil and module are doing their job. If there are no pickup pulses to the ECM will not send commands to the fuel injectors. No pulses, no fuel, no run. Let's go back to the distributor for a minute. There are a few more things I'd like to tell you about. First of all, the distributor has no ignition coil as part of the cap. The coil is mounted remotely. Also, there is no vacuum advance unit mounted on the distributor or centrifugal weights on the inside. It is truly electronic in nature. Instead of the old mechanical stuff, we find the pickup coil and the HEI module. Though the module looks the same as the pre-TBI module, they are not interchangeable. We've already discussed these two items and what they do in the ignition system, but let's just go over them once more in a little more detail. You know and I know if you're going to fix something, it's a whole lot easier if you know how it works. Matter of fact, with that kind of knowledge, we can probably fix it right the first time. Let's talk about the pickup coil first. It's a signal generator. As the distributor rotor turns, the pickup coil generates a voltage signal that goes to the HEI module. The pickup coil issues 3 or 4 reference pulses to the HEI module for every revolution of the crankshaft, depending on if it's a V6 or a V8. The HEI module, on receiving these pulses, converts them to a square waveform that the ECM can use. These signals are pretty important, for as we said a few minutes ago, no signal, no run. In addition to using these signals to trigger the fuel injector pulses, the ECM also uses the pickup coil signals to generate the ignition coil spark signal, to calculate engine RPMs, and to know crankshaft position. That covers the pickup coil, and we've mentioned the HEI module. The HEI module has 3 major functions to perform. The first is what we just talked about, converting the pickup coil signal to a square waveform for the ECM. The second function is to act as a switch that functions above and below a certain RPM threshold. We talked about this function when we discussed switching from the bypass mode, used for starting, to the EST mode, used for normal engine operation. The third and last function of the HEI module is to fix spark timing to a predetermined advance curve. This is used during the bypass mode and during the drive-home maneuver if the EST system fails. There are 4 terminals on the HEI module that mate with the electrical connector wired to the ECM. On the connector, they are labeled A, B, C, and D. Again, each of these circuits leads to the ECM. Let's go over the 4 circuits by their function. Terminal A, called the reference ground low, is grounded in the distributor and is used to make sure the ground circuit has no voltage drop that could affect performance. Terminal B is the bypass terminal. At a little over 400 RPM, the ECM applies 5 volts to this circuit. As we've seen, that switched the spark timing control from the module to the EST system, or put another way, from bypass control to ECM control. Terminal C, or the distributor reference high, provides the ECM with RPM and crankshaft position information. Remember how the HEI module laundered the pickup coil signals into nice square waves the ECM could digest? And then there is terminal D, the EST terminal. This circuit triggers the module. The ECM does not know what the actual timing is at this point, but it does know when it gets the reference signal. It then advances or retards the spark from that point. From a diagnostic standpoint, you can see that if the base timing is set incorrectly, the engine spark curve will be incorrect. While that just about concludes the ignition system discussion, there's still one more element that affects the spark timing that we should cover: spark knock. We said that knock occurs when the spark plug fires too soon, that it's the result of the combustion pressure front colliding with the upward moving piston. The fix for this condition is to retard the spark a bit. Here's what happens. There is a system on all the truck engines we've been talking about, except the 7.4 liter, called the electronic spark control, or ESC. It's got two major components: the ESC module and the ESC knock sensor. The knock sensor is located in the engine block near the cylinders, where it can detect abnormal vibration or spark knocking in the engine. The ESC module receives the knock sensor information and sends a voltage signal, 8 to 10 volts, to the ECM when there is no spark knocking being detected by the knock sensor. In this case, the ECM orders normal spark advance. When spark knock occurs and is detected by the knock sensor, the module turns off the circuit to the ECM. With zero signal voltage, the ECM retards the electronic spark timing to reduce the spark knock. Once again, the electronic spark control is not used on the 7.4 liter engine. Seeing the information presented here, you should have a pretty good idea of what the ignition system is and what it does in today's modern electronically controlled engines. A lot of the stuff in this tape carries over to many other current GM engines, with some important differences, of course. The next and last tape in this series of 4 is Diagnostics. So get out your service manual and dust off the scan tool. Have a good one. Hope to see you then. Introduce you to the 4th tape in this series on the 4.3 liter V6 and the 5, 5.7, and 7.4 liter V8 truck engines. It's called Diagnostics. We've now gone through 3 tapes together. In the first, you received an overview of the systems used on our 4 truck engines. In the second tape, we zeroed in on the TBI 220 and the fuel system. The ignition system was the subject of the 3rd tape. In all these tapes, our objective was to learn as much about the engine's components and how they work as possible, particularly the ones associated with the ECM. There is no better diagnostic tool in the world than a good understanding of the item you're trying to fix. If you know what it's supposed to do and how it does it, you'll save yourself a lot of wild goose chases. That's why we've said from time to time during this tape series how important it is for you to understand the systems and components of the 4 engines presented here. The first step in diagnosing a problem under the hood is to make sure the obvious stuff is okay. Check out the vacuum hoses for splits and kinks. Make sure they're connected right. Look for air leaks at the throttle body mounting and around the intake manifold. Ignition wires can be bad. Look for cracking, hardness, proper routing, and carbon tracking. Check wiring for proper mating of connectors. Look for corrosion. Are there pinches or cuts in the wiring? That stuff may sound elementary to you, but you know, it happens every day. Just check things out for a moment before you start changing parts. The few minutes you spend doing this up front could save you hours later on. We've already seen how the ECM controls just about everything in the engine compartment. It knows what's going on and can tell you about it if you ask it right. There are two ways you can talk with the ECM. The first is through the service engine soon light, and the second and better way is by using a scan tool. Let's look at each method. First, the service engine soon light way. You begin the diagnostic check by inserting a jumper wire between ALDL pins A and B with the engine off and ignition on. The service engine soon light should flash once, pause, flash twice, then repeat the sequence twice more. It's flashing a code 12. That tells you the ECM's diagnostics are working. Any trouble codes stored in the ECM will begin flashing after the code 12. If no codes are stored, it will continue to flash the code 12 sequence. We have disconnected the coolant temperature sensor, and the service engine soon light is now flashing a code 15. The coolant sensor circuit low temperature indicated code. If you look that code up in the service manual, you'll find all sorts of help in fixing the problem. We'll go into that later, since this is just a demo on how the service engine soon diagnostic system works. Now, let's just take a look at a scan tool, in case you're not familiar with it. For our demonstration, we'll use Tech 1. Be sure to read the manual that comes with this tool. First, make sure the ignition is off. Then push the scan tool plug into the ALDL connector and plug the power cable into the cigarette lighter with the engine off and ignition on. Remember, we just read a code 15 when we disconnected the coolant temperature sensor using the jumper method. Well, here's the same code 15 on the scan tool. We still haven't reconnected the coolant sensor. Now, let's take just a minute and talk about codes as they apply to our four engines. There are 20 different codes, in addition to the code 12 that tells us the ECM's diagnostics are working. And they cover just about any hard ECM system failure you can imagine. Occurrences of any of these failures will result in the service engine soon light going on with the stored codes waiting to be read out by the technician. A stored code will be erased if the problem does not reoccur within 50 engine starts. With some customers, 50 starts might take a while, so it's a good idea to check and make sure the codes you read out are active. And here's how you do that. When you first read the codes, write them down as they come up. Now, clear the ECM's memory. You do this by disconnecting the battery or by removing the ECM's fuse for 10 seconds or so, then reconnect. Start the engine and let it run for a few minutes, or until the service engine soon light comes on again. Now, shut down the engine and reread the codes with the scan tool. If you get the same codes again, you can be pretty sure that a problem exists. One other thing you'll want to watch out for, some codes will only be set if the truck is driven or the rear wheels jacked up. Code 24 for the vehicle speed sensor is a good example. What we've discussed so far, then, is how to get the ECM to talk to us about its problem. We've seen we can do this in two different ways. We can do it by using a jumper between the ALDL pins A and B and counting flashes on the service engine soon light. Or we can do it by using the scan tool, which is a lot easier and more versatile. Now that we have the trouble code numbers, we can go to our service manual for guidance on how to fix the problem. Now, since you have the code readout, take the next step in diagnosing the problem. Read the service manual. You don't have to read the whole thing, just the few pages that apply to that code number. It can really help you identify and fix hard failures, the kind that set the code. And it will usually also help you with the tougher intermittent failures. There have been thousands of hours spent putting those manuals together just for you. They've been researched, tested, and written by teams of specialists in electronics, engineering, and systems operations. And they will work. Remember the code 15 we read when we disconnected the coolant sensor? You'll find it under code 15, coolant sensor circuit low temperature indicated, in the computer command control section of the GMC truck service manual. In this example, we are working on a 1988 truck, so be sure and use an 88 manual. It's the same as the 87 manual. In fact, always make sure you have the right manual to go with the model year of the vehicle you're working on. That way, any little changes that take place in a system from year to year will be accounted for and save you time. The two diagnostic pages on code 15 begin with a circuit diagram showing how the coolant temperature sensor is wired into the ECM, right down to the color of the wires and terminal numbers. On the facing page, there is a diagnostic chart that, starting with step 1, will lead you to a solution to the code 15 problem. You would have found our disconnected coolant sensor when you went to step 2 on the chart. All the codes are presented in this easy-to-use manner in the GM service manual, so use them. They'll help you a lot. There's another area in the chain of events when servicing a vehicle that ought to be mentioned. That's the repair order written by the service writer. Instead of just scribbling "won't start" on it, question the customer about when and how it won't start. Is the weather hot or is the weather cold? Is the engine hot or is the engine cold? Does it start sometimes and not at others? Obtain and write down all the information you can. All these bits of information are important clues when the technician gets ready to start work on a vehicle. It's just like a patient telling a doctor their symptoms. That goes a long way toward helping the doctor diagnose the patient's problem. And it'll go a long way toward helping the technician diagnose a vehicle's problem. Okay, we've said we need a well-written and complete service order. We've seen how to read codes by two different methods, the jumper and the scan tool. And we've learned how to go to the service manual to get valuable help in solving a problem. Now that we have an idea of what we're trying to do, let's go through the diagnosis of the 4.3, 5, 5.7, and 7.4-liter truck engines in more detail. We'll start at the beginning. The computer command control system has a diagnostic system built right into the ECM to show a failed circuit. Its indicator is the amber service engine soon light. It will light up if a problem is detected while the engine and vehicle are running. The light is also used as a bulb and system check. With the ignition key on and the engine not running, the light should be lit, showing you have a good bulb, and that the ECM has completed the circuit to the bulb. When the engine is started, the light should turn off. If either of these conditions does not happen, the cause must be found and corrected before any further diagnosis takes place. There are troubleshooting flow diagrams for both these conditions in the repair manual. Once the service engine soon light is functioning properly, the ALDL connector can be used with either the jumper or the scan tool, as we showed you a few minutes ago. So far, we've only mentioned terminal A and terminal B of this connector. A provides a ground circuit for the other 8 active terminals. Terminal B, as we've seen using the jumper, is the ECM's diagnostic terminal. Connect it to A and the codes start flashing with the key on and engine off. Terminal C is used to diagnose the air management system. It's wired to the ground side of the electric air control valve on the 4.3, 5, 5.7, and 7.4 truck engine. Grounding this diagnostic terminal will energize the valve solenoid if the ECM and circuits are normal. This condition can be read with a simple test light. If the bulb lights, everything is okay circuit-wise, including the solenoid. You'll find this check, plus many other checks that are non-electrical, in the diagnostic diagram in the service manual. Terminal D is not used on this series of engines. Terminal E is the serial data line and is used by the scan tool to read various system data information, codes, system voltages, block learn values, all those things. The next terminal, terminal F, is used to diagnose the torque converter clutch system, and it's wired to the ground side of the TCC system. It may be used with a test light to determine if the clutch circuit is okay when you don't have a scan tool handy. By the way, this applies only to the 4.3, 5, and 5.7 liter engines. Terminal G, that's used to diagnose the fuel pump circuit on the C and K trucks. By applying 12 volts to the terminal, the fuel pump will run with the ignition key off. Listen to find out if the pump is operating. It's a good way to check out the pump all by itself. Other trucks have a pigtail at the fuel pump relay to check the pump. If the pump is okay, it's time to go to the service manual diagnostic chart. It leads you through the further steps you need to follow to get to the problem so you can fix it. Terminal H has to do with diagnosing the brake system outside the scope of this tape. The last terminal, M, does not apply to the engines we're talking about. That wraps up the ALDL connector. Now, let's talk about the scan tool and what it can do for you. We've already seen how you plug it into the cigarette lighter and the ALDL connector. And we've seen it reads out ECM system problem codes. While we're on the subject, remember to clear the codes after you've made the repairs. That way, the next technician that works on the truck doesn't have to plow through a bunch of stuff that's already been fixed. That next technician could be you. Today, we'll be using a Tech 1, a versatile, handheld diagnostic computer, a scan tool. It was designed specifically to help you diagnose and repair General Motors electronic systems. Those can range from 1981 to the current model year. It's important that you read the manual that comes with your scan tool. That way, you'll be sure the data you get from it is the right stuff. It not only gives you codes, as you've seen, but it can also give you visual readouts of most inputs to the ECM and some outputs. There are two types of information the scan tool can receive and display: discrete parameters and analog parameters. Now, those are $50 words and enough to make any of us a little nervous. Discrete parameters deal with information that can only be provided in one of two distinct ways. For example, open or closed loop, on or off in case of a switch, yes or no in whatever situation. You get the idea. Analog parameters are used to define quantities: engine speed in RPMs, oxygen sensor voltage, coolant temperature, that sort of thing. Here are a few examples of items other than codes the Tech 1 will read out for you. AC clutch, displays on or off, integrator and block learn memory, displays the cell the ECM is using, closed or open loop, coolant temperature in degrees centigrade, injector pulse width, the on time being given in milliseconds, knock retard. In number of degrees, the EST is retarded. Knock signal, whether knock is present or not, and map signal readout as a voltage. You can see that when you're diagnosing a problem, if you can get the ECM to tell you the kinds of values you need, You have a powerful tool in your hand, and the Tech 1 can do just that. When and how to push what buttons on the Tech 1 to get the information you want is the subject of a fair-sized manual, so we can't cover it all in this half-hour tape. However, you don't have to read the whole thing. It's just like the service manual. Read and use only the parts you need for the problem at hand. We will use the scan tool in a few minutes when we go through checking out some of the ECM sensors and the ECM itself. You'll see how versatile and helpful it can be. We have talked about the diagnostic mode, where we have received our stored codes from the ECM. They were obtained with the ignition on and the engine stopped. While we were in that mode, the ECM was doing a couple of other things. It energized all ECM-controlled relays and solenoids except the fuel pump relay. And the idle air control is also moved to its fully extended position. There's another mode, however, we need to talk about now, the field service mode. In this mode, we can tell if the engine is running in closed or open loop. To get into this mode, the A and B terminals are grounded in the ALDL, and the engine is started. While the engine is in open loop operation, the service engine soon light flashes 2.5 times per second. When the engine goes into closed loop, the light flashes only once per second. Also in closed loop, the light will stay out most of the time if the system is too lean, and on most of the time if the system is too rich. While the engine is in the field service mode, it won't store codes, and the closed-loop timer is bypassed. Of the 20 codes the ECM can store, 13 of them are most easily diagnosed using the scan tool. This is done by following the diagnostic chart in the service manual and taking readings with the scan tool when the chart tells you to. Those readings can then be compared to the value given on the chart. If they don't agree, you're well on your way to finding the trouble. Let's look at an actual example. The truck owner has brought this vehicle in to be looked at because his service engine soon light has come on. The service writer, in talking to the customer, has found little to go on. The owner has no complaints about drivability. He just brought it in because the light was on. The first step, then, is to plug the Tech 1 into the ALDL, and let's see what codes have been set. There's a code 45. Well, let's look at the service manual and see what that's all about. Here it is, code 45, rich exhaust indicated. And across the top of the diagnostic page are the words, scan diagnostics. We see by looking at the wiring diagram, this failure concerns the O2 sensor circuit. You'll remember from earlier tapes, the O2 sensor in the engine exhaust manifold changes its output voltage due to a chemical reaction with the oxygen in the exhaust gas stream. The more oxygen present in the exhaust, the lower the voltage produced. The output voltages range from 0.1 volts for a lean mixture to about 1 volt for a rich mixture. Therefore, a rich exhaust, as our code 45 calls it, means the O2 signal should be about 0.9 volts. You'll also remember the sensor has to be hot, about 600 degrees Fahrenheit, for it to operate at all. Step 1 on the diagnostics chart is to run the engine at 1200 RPM and be sure the engine is warm, 75 to 95 degrees centigrade. By following the scan tool manual, you'll be able to check out these two parameters as shown here. Next, adjust the scan tool to read out the O2 sensor voltage. We find it is fixed above 0.75 volts or 750 millivolts, indicating a rich mixture. Our diagnostic diagram then directs us to disconnect the O2 sensor and jumper that lead wire to ground. At this point, the scan tool should display a reading below 0.35 volts or 350 millivolts, and it does. If it had not, the diagram would have directed us to replace the ECM. Did you notice that the diagram never mentions to replace the O2 sensor? Why? Because right from the beginning of the diagnosis, it was sending a high voltage signal, which meant it was all right. Since it did read below 0.35 volts, we are directed to a series of diagnostic aids on the page facing the diagnostic chart, but first reconnect the O2 sensor. Once more, using the scan tool, get into the block learn readout mode. The scan tool can observe the values in each of the block learn cells. Before we start this, let's just do a quick review of block learn, just so we're all starting from the same spot. Block learn, you'll remember, was located in the ECM and divided into 16 individual memory blocks, or cells. They are arranged in a 4x4 grid with map or load on the vertical axis. The horizontal axis shows RPM. You can see that any combination of load and RPM falls within one of these cells, from low RPM and low load to high RPM and high load. Also, each block has an initially assigned value or count of 128. And you'll recall that is the same as the integrator's no correction count. The integrator makes short-term injector pulse width corrections based on O2 sensor output. After a given number of excursions from 128 by the integrator, the appropriate memory cell in block learn matching those engine conditions changes to a new value on a long-term basis. Looking at the block learn cell values with the scan tool can tell you under what engine operating conditions the trouble code has been set. In this case, code 45, rich exhaust indicated, the value in block learn will be about 115. That tells us one thing. Whatever it is that's setting the code does it under all engine operating conditions. The repair manual lists 9 different items you can check to find what caused the code. The first item tells us to check fuel pressure. The system will go rich if fuel pressure is too high. Remember, the injectors are on for a set amount of time. That means if the fuel pressure is higher than spec, more fuel will run through the injector than the engine requires, or the integrator can compensate for. This can be caused by a faulty pressure regulator on the TBI 220. A leaking diaphragm, instead of regulating at 9 psi, would permit full pump pressure, around 15 psi. On the TBI 220, the pressure regulator is serviced as part of the fuel meter cover. So replace the fuel meter cover assembly. That should fix the problem. The next step is to clear the stored code 45 by disconnecting the battery or by removing the ECM's fuse for 10 seconds or so, then reconnect. To prevent damage to the ECM, be sure the ignition is off when you disconnect or reconnect it with the battery. Now, start the engine and determine that it has gone to closed loop operation after a minute or so, and that the service engine soon light is out. We got a little lucky on that one. What if it had not been the pressure regulator? Well, the manual gives you some other ideas for finding the cause of the code 45. We could have checked for a leaking injector. Since it's under constant pressure and leaking, a good bit more fuel could be forced into the throttle body than the amount admitted with the ECM pulse alone. Again, a rich mixture. If the injectors and the pressure regulator were both okay, then it would be time to move on to other possible causes, not parts of the TBI 220. The service manual suggests you check out the high-energy ignition shielding. An open ground in the ignition system reference low circuit can result in induced electrical noise, sometimes called EMI, or electromagnetic interference. The ECM mistakes this noise for reference pulses and believes the engine is going faster than it actually is. After all, it only knows what it's told. Since this is the case, it increases the frequency of the pulses to the injectors, and here again, we have too much fuel going to the engine for its actual operating conditions, or a rich mixture. The engine tachometer will also show a higher than actual engine speed, which can help in diagnosing this problem. The next step would be to check for fuel saturation in the canister. If for some reason it's loaded with vapors and even raw fuel, when the engine begins to purge it, a lot more fuel will enter the engine than is intended when the system is working to spec. A careful check of the canister control and hoses against the service manual is in order. Another possibility for a rich exhaust code is a faulty map sensor that causes the ECM to believe a higher than normal manifold pressure exists, and that can cause a rich mixture. Disconnecting the map sensor will allow the ECM to set a default value for the map sensor. If the rich condition goes away while the sensor is disconnected, replace the map sensor. One last tip from the service manual on a set code 45. Check out the TPS or throttle position sensor. An intermittent TPS output can cause the system to go rich. This is due to a false indication of the engine accelerating. That concludes what the service manual has to say about code 45. You can see that the diagnostic techniques laid out for you are pretty thorough. There's no doubt you would have discovered the cause and fixed the problem of the code 45. All the other codes are treated in the same way in the manual. By using the scan tool and following the service manual, you'll find your job a lot easier. What we have tried to get across here is diagnostic service techniques that will help you solve problems time and again. We stress that the first thing you always do is check out the engine for loose or corroded connectors, broken or frayed wires, leaky hoses, all the visual stuff that's easy and quick to do. 9 times out of 10, that'll take care of your intermittent troubles right there. The next item is to get handy with the scan tool. Practice with the tool. Follow its manual till you know what it can do like the back of your hand. To pick the electronic brain of today's ECMs, you have to have this capability. Without it, you're like a plumber without a wrench. Once you're up to speed on the scan tool, take full advantage of it by using it with the service manual. Read the 2-page write-ups on the codes after the scan tool pulls them out of the ECM for you. They will save you a lot of time and give you some hints that, if followed, are almost sure to help you solve your diagnostic problem. That's all great stuff, but the most important ingredient is you. It's your knowledge and skills that make it all work. That's why we've emphasized in all 4 of these tapes, learn the systems and their components. Learn how they work. You really can't fix them unless you know what they're supposed to do and how they do it. You know, and it's just my opinion, if you understand how to use the scan tool and service manual together, and you know the system's cold as shown in the first 3 Expertec tapes of this series, you'll probably never need to look at this diagnostic tape again. You'll have everything you need right up here. Thanks for watching.